Okay, we are at 9.6, the center of mass. Let's go ahead and share the PowerPoint. We'll be doing some center of mass experiments when we study torque, but we'll go ahead and introduce it here. I wish they showed a blow up of this pair of masses, the blue one and the kind of a tan one, connected by a very light rod. The tan one is a larger mass. Let's say they're uniform density each. The tan one is a larger mass than the blue one. So the center of mass is located somewhere where the X is. So if you were to push on the near the upper blue one, it would rotate to the right. It would kind of topple over. Now, if you were to push below the center of mass, the system rotates counterclockwise when a force is applied below the mass. So above, it rotates clockwise. Below, it rotates counterclockwise. If you were able to push right on the X, the center of gravity, the system moves in the direction of the force without rotating when a force is applied at the center of mass. It's one way to find the center of mass, but we'll have other ways. We'll have a calculated way. And here's they switch now the ball is the bigger one. The blue ball is the bigger one. And the center of mass is mass 1 times the distance x1 from the origin, and plus mass 2 times x2 from the origin, divided by the total mass, m1 plus m2. Now, if x1 is equal to 0, then x2 becomes d, just the distance between them. And let's say m2 is equal to twice m1, then the center of mass is equal to m times 0 plus 2m d, 2m1 d, and m1 plus 2m1. So it's about 2/3. It's two-thirds of d. It's 2/3 of the way over. Okay, now for multiple systems, we do the same thing. We do m1 times some x1 plus m2 times x2, m3 times x3, all the way to mn times x sub n. The sum of all those divided by the total mass. You sum all of those masses together. So the sum of mi xi divided by the sum of mi equals, the bottom becomes a total m. We use capital M to indicate the total mass. So the center of mass is really the sum of all the individual masses from their distance from some point divided by the total mass. And it's the same for that's in the x direction. For the y direction, the y center of mass is 1 over m times the sum of mi yi, and the z center of mass is 1 over m times the sum of mi zi. Okay, so the center of mass, r center of mass, is equal to the x center of mass I hat plus y center of mass j hat plus z center of mass k hat. And we can see that that's there's 1 over m in all of those. 1 over m times the sum of mi xi I hat plus 1 over m times the sum of mi yi j hat plus 1 over the total mass times the sum of mi zi k hat. So R is equal to the R center of mass is equal to 1 over m times the sum of mi ri. Okay, and so ri is equal to xi I hat plus yi j hat plus zi k hat. Okay, now let's extend it from this was a bunch of individual particles. Now let's just extend it to just a mass, and we can consider small elements of mass, delta mi, for at different positions throughout the mass region, r sub I, so that the center of mass is approximately 1 over mass, the total mass, times the sum of xi delta mi, all these little elements of mass throughout this region. Now, it's exactly equal to the limit as delta mi approaches 0 of 1 over m xi delta mi, or we can say the integral equals 1 over m times the integral of x dm. And in the y direction, it's 1 over m times the integral of y dm, and for the z, center of mass, 1 over m times the integral of z dm. So the r vector center of mass is equal to 1 over m integral of r dm. Okay, now we're talking about the center of mass. Now we're going to talk about the center of gravity. The center of gravity, if you take a point and you imagine it as being concentrated at the center of mass times the gravitational acceleration, you get the center of gravity. And you can determine the center of gravity for a uniform object. It's pretty easy to find the center of gravity. You can, if you have like a rod, you can, it's pretty much through the axis of symmetry and pretty much right in the center. But what if you have an odd shaped object like this wrench? Well, you can suspend it from different points, and if you draw a line vertically through the suspension point, where all of those intersect, if you do different suspension points, the intersection of the center line through the suspension line will give you the center of mass. Let's read the boxes. The wrench is hung freely first from point A and then from point C being on the end. You can see there at the lower picture. The intersection of the two lines AB and CD locates the center of gravity. Okay, here's a quick quiz. A baseball bat of uniform density is cut at the location of its center of mass as shown in the figure. Which piece has a smaller mass? Now, you probably intuitively you would just think, oh well, they're both the same, but that's not correct. The piece on the left is actually smaller because of the distribution of the masses. The piece with the handle will have less mass than the piece made up of the end of the bat. You take the origin of the coordinates as the center of mass before the bat was cut, and replace each cut piece by a small sphere located at each piece center of mass. The sphere representing the handle piece is farther from the origin, but the product of the less mass and greater distance balances the product of greater mass and less distance from the end piece as shown. I think we'll see that more as we do an experiment on torque. So the piece on the left, I hadn't showed that. Okay, systems of many particles. We'll save that for the next. Section. That's 9.7.